Welcome back to day 2 of our low level design course. In today's session, we are going to refresh and strengthen our understanding of object oriented programming, commonly referred to as OOP. This isn't just a theoretical detour. OOP concepts are the foundation of everything we will be doing in system design going forward. Whether you are modeling a simple object like a book or designing a scalable system like the ride hailing platform, understanding OOP deeply will help you make better architectural choices. So let's get started. Here's a quick look at today's agenda. We will start by understanding what object-oriented programming really means and how it differs from other paradigms. Then we will take a deep dive into the four pillars of OOP: encapsulation, abstraction, inheritance, and polymorphism. We will discuss common pitfalls, compare composition with inheritance, and look at where OOP fits into real-world low-level design. We will also get a hands-on task to apply what we have learned and some homework to reflect on our understanding. Let's go step by step. Object-oriented programming is a way of thinking about and structuring software that mirrors how we think about the real world. It organizes code around objects, self-contained units that encapsulate both data and behavior. For example, instead of thinking in terms of raw procedures and functions, in OOP we think in terms of entities like user, order, or invoice, each with their own characteristics and operations. This leads to modular, testable, and reusable code. OOP stands in contrast to procedural programming, where logic and data are often separated. Here we bring them together to form logical units of responsibility. OOP has four foundational pillars that every developer must master. First is encapsulation, which protects internal state and exposes only what's necessary. Second is abstraction, which lets us simplify complexity by focusing only on essential behavior. Third, we have inheritance, which allows us to create hierarchies and reuse code. And finally, polymorphism, which enables a single interface to represent different underlying forms. These concepts aren't just academic, they are used in every well designed system, from frameworks to APIs to entire architectures. Encapsulation is the idea of hiding the internal details of an object and exposing a clear, controlled interface. Think of a bank account class, its balance is private. You can't change it from outside. Instead, you have to use a deposit or withdraw method. This protects the object from being put in an invalid state. Encapsulation also makes systems easier to refactor because internal changes don't ripple out to everything that uses the object. In design terms, this means building strong walls around our objects. Only the doors should be public. Abstraction is about focusing on what an object does, not how it does. For example, when you use a payment method in an app, you don't care about how UPI or credit card processing works behind the scenes. You just care that it gets the job done. In code, this often shows up as interfaces or abstract classes that define a contract, and then specific classes implement the details. Abstraction reduces cognitive load and improves flexibility. It's like driving a car, you use the pedals and steering wheel, but you don't need to understand how the engine works. Inheritance allows one class to reuse the behavior of another. For example, you might have a base class vehicle and car and truck classes that extend it. They inherit the common behavior but can override or extend it as needed. Inheritance saves us from duplicating code, but it can also create tightly coupled structures that are hard to change later. That's why we use inheritance when it represents a clear, easy relationship, but don't overdo it. If things start feeling too rigid, composition might be a better choice. Polymorphism is a powerful feature of OOP that lets us treat objects of different types through a common interface. Imagine you have a list of shapes: circle, square, triangle, and you want to draw each one. You don't need to know the exact type of shape, you just call draw, and the right implementation runs. This makes your code extensible. You can add new shapes types without changing the existing code. It also improves testability and adherence to the open close principle, which we will cover slowly. This is a topic that often sparks debate. Should you use inheritance or composition? Inheritance models an easy relationship, like dog is a mammal. Composition, on the other hand, models a has a relationship, like car has an engine. While inheritance can be elegant, it also creates tight coupling and a rigid class hierarchy. Composition gives us more flexibility and decouples the components. In modern design, we often favor composition because it results in more maintainable and scalable systems. Now it's your turn for today's hands-on challenge. I want you to design a basic video streaming application. Think about the core entities like user, video, playlist, and subscription. How would you model their relationships? What properties and behaviors should they have? Try to incorporate all four OOP principles: encapsulation for private data, abstraction for clean interfaces, inheritance where it makes sense, and polymorphism to allow flexible behaviors. This task will help solidify your conceptual understanding with practical application. OOP is a powerful tool, but like any tool, it can be misused. One common mistake is overusing inheritance, creating deep and brittle hierarchies that are hard to maintain. Another is breaking encapsulation, exposing internal fields or allowing external classes to manipulate object state freely. Developers also often confuse abstraction with generalization, leading to ambiguous designs. And sometimes interfaces are introduced without clear contracts. Always aim for clarity, minimalism, and cohesion in your design. In real-world low-level design, OOP is everywhere. When we draw class diagrams, define modules, or write interface-driven code, we are applying OOP principles. For example, a logging framework might expose an abstract logger interface with implementations for console, file, or network logging. This allows us to plug and play components with minimal changes. OOP not only helps organize code, it lays the groundwork for extensibility, testability, and design pattern usage, all of which are critical in large systems. For your homework, I would like you to design a basic banking system. Think about the core classes you will need: account, customer, transaction, and try to model their attributes and behaviors. Use encapsulation to protect data, abstraction to expose meaningful operations, and consider how polymorphism or inheritance might apply. Reflect on what trade-offs you are making. This exercise is not about getting a perfect answer, but about developing your design intuition. To wrap up, object-oriented programming is not just a buzzword, it's a mindset. It teaches you how to think in terms of real-world entities, organize your logic around them, and build systems that are robust, modular, and future-proof. The four pillars: encapsulation, abstraction, inheritance, and polymorphism will show up again and again throughout this course. In our next session, we will build on this foundation by exploring the solid principles, guidelines that help you apply OOP in a clean, scalable way. See you there.